All right, so this is going to be a wrap up for the second part of the lab, which is elastic potential energy. Okay, so this is the EE part 2. All right, and in this lab, what you did as a wrap up for your super summary, right, you had a spring with a certain amount of mass on it, and you kept adding mass to the spring, and then you saw how far the spring would stretch, okay? And then you made basically a graph. Eventually, that was the spring stretch, X in meters, and the force of tension in newtons. Okay, and you got your numbers, and then you made your graph. Okay, so this was spring stretch, which is usually called X, right? It's also a distance, right? And then this should be force in newtons. Okay, and ours was actually force of tension, really. Okay, and you had a force diagram of your mass. Well, that doesn't look so balanced. Try to make that a little, okay. When it was hanging at the bottom, so it wasn't moving, so the forces should have been balanced. There was a tension force up from the spring and a gravity force down from the earth, okay? This is all stuff that should be on your whiteboard. All right, when you actually made the graph, it should have looked pretty linear, something like this, okay? And if I write the equation of it, I can start with y equals mx plus b because it's a line, all right? Then the y-axis variable should have been force of tension, okay? Your slope should have been some number between like 3 and 30, all right? If you got a slope that was point something, or if you got a slope that was in the hundreds, you did something wrong. You need to go back and fix it, okay? So your slope should have been in like the 10s, 20s, 30s, something like that. So if it wasn't, that means you did it wrong. All right, so I'm going to just make up, say my slope was 16, and then I need the units for the slope. Okay, so slope is always a rise over run. Rise over run. Ooh, that doesn't look so good. So the units should be newtons is the rise, meters is the run. All right, so slopes always tell relationships between the variables, so it's going to have both variables in it, because it's going to be 16 newtons, 1 meter, 16 newtons, 1 meter, 16 newtons, 1 meter, okay? So that's my slope. The x variable in this case is just still called x, because that's what we call spring stretch, all right? And then plus your y-intercept should have been very close to 0, but you may have gotten something that wasn't perfect, probably. Let's say you got 0.02, and since it's a y-intercept, it should be newtons, because it's the y variable, okay? So somewhere on your whiteboard, this should be your equation, okay? This also is going to go in your super summary. I might try to copy off a picture of that and see if I can do that. Okay. All right. Just in general, when you're explaining this slope, all right, is telling you something about the spring, all right? So if the slope is 16 newtons per meter, what does that mean about the spring? Okay, so for every 1 meter that what? Whoa, the spring stretches, it takes, or it provides, depending on which side you're looking at it from, 16 newtons of force. Okay, all right. This number here is telling us something about the spring, okay? So like you could have one that would be 5 newtons per meter or 5,000 newtons per meter, all right? This spring would only take 5 newtons to make it stretch a meter. 5 newtons is not very much force. You could push that with your hands. 5 newtons is not very much. It could stretch a whole meter if you pull or push it 5 newtons of force. But this spring would take 5,000 newtons of force, okay, to stretch it a meter. So that means that this spring would be very strong. This spring would be very weak, all right? So this value, the slope, its symbol is little k, lowercase k, and it's what we call the spring constant. Okay, some books will call it the force constant because it doesn't have to be a spring. It could be a rubber band or anything stretchy, but I don't know, I learned it as spring constant, so that's what we're going to go with, okay? So this number, little k, is called the spring constant. It's basically telling you the strength of the spring. Okay, a little number makes the spring weak. A big number makes the spring strong. Okay, all right. So then using this equation then, right, we can do force of tension equals, instead of 16 newtons per meter, we can call that little k, right? Because that could be anybody's. 16 was my spring constant, but yours might have been 3 or 30 or 25 or 13. So we just put k in because that means it could be anyone's spring constant, okay? Times x, all right? And then this y-intercept should be 0, right? Because that would make sense, because if you have no force, right, you don't put anything on it, you don't pull it at all, there is no spring stretch. Okay, so we're just going to go away. So the equation that we get is this in general, okay? And this is what is called Hooke's law, which you don't need to know exactly what it's called, but just so you know, that's what it's called. Okay, that's called Hooke's law. Okay, all right, let's think what else might need to be in here. Okay, anything else about the line? Forget anything? I don't think so. Okay, so that's all the stuff about the line. Now, the real part that we care about is the area, because that's what this whole lab is about, is the different areas, okay? Did I switch to that? Okay, all right. So if I take my highest point, okay, let's just say mine was 0.07 and 2. I don't know what yours was. Okay, seems reasonable, okay? And I shade in this area underneath the line, just like I did before, okay? I'm going to get something that's going to be like a Newton times meter. That's the unit for energy, okay? Just like we saw before. This is going to be the same in all parts of the lab. This is how it's going to go, all right? So then what you're going to have is the area is going to be 1/2 base times height, because this one's a triangle, okay? And then you're going to need to calculate it. So this should be on your whiteboard, I hope. Okay, 0.07 meters. If it's not, you might need to make a little addendum and add it, okay? Times 2 newtons. Okay, so for me, this is going to be what? 1. Oh, that's easy. That was convenient. 1/2 times 2 is just 1. Okay, so I'm going to get 0.07 meters times newtons. That's a joule. Okay, that again, when I look at the units, that's how I know that this is an energy, because the units are in joules. That means it measures an energy. Okay, so when I stretch the spring this much, okay, to 0.07 meters, that is going to store 0.07 joules of energy. Okay, all right. If I want to write it as the actual equation, okay, I know the area is the energy stored, 1/2. The base of the triangle is x, and the height of the triangle is f, okay, or ft in this case. Okay, that's not wrong. It's just not how we normally write it. Normally you'll see it like this, 1/2 x, and instead of this f, do you see how ft is also the same as kx, based on the equation that we did before? So we do kx, and then if we clean it up, 1/2 kx squared. This is normally the way that you see the energy elastic equation. 1/2 k, which is the spring constant, times the spring stretch squared. All right, and then that's the equation for elastic potential energy. Okay, all right, a couple other things in the CER that I remember that they asked for. Let me pause it for a second, see if I can open that up. Okay, so here goes the super summary. So you're going to make sure that you're going to put your Desmos graph in. Make sure it has units on both and labels on both, okay? So it should have been FT in newtons, okay, and X in meters. Have your line. Make sure you have the little information about, that has the data table and the equation, okay? All right. Mathematical relationship between the variables, okay? This is describe the shape of the graph and the relationship, and you're also going to put the equation here, okay? So you're going to rewrite your equation, whatever yours was. X plus, this was mine, okay? And when I look at the graph, what kind of a shape is it? Okay, it's a line, so it's a linear shape. Okay, and the relationship between force and displacement is what? What is that called? Remember, the special kind of linear when it has a y-intercept of 0. Direct, or you can say direct variation. Okay, make sure you write this in your own words, right? You're not just copying mine. Okay, so that's what should be in this box. Okay, in this one, I think you can figure it out. You're going to use the two variables, ft and x, and then you're going to choose increases or decreases, right? So just cross one of them out and clean up the sentence. Okay, so that you're just going to plug that in. That should be pretty easy. Okay, quantitative relationship between the variables. What does the slope of the line represent? Okay, 16 newtons per meters. Okay, what does it mean about the spring? You can look at what we just talked about in the video before. Okay, and what is it called? Remember, it has a name and it has a letter, right? And what does it mean? That's what we talked about in the last page. So I'm going to let you figure that out. Okay, but that's what's going to go here. Okay, and then the prediction example, right? The purpose, why is this freaking out? The purpose of writing an equation is so that you can use it to find out other values that you do not know. Okay, so you're going to start with your equation. And for the prediction example, you're going to choose a spring stretch. Okay, so I'll just pick one, whatever, 0.02 meters or whatever. Okay, all right, and then you're going to solve out and then find out how much force would that have taken. All right, so in order to stretch the spring by a certain amount that you choose, what force would be required? Okay, so that's what's going to go there. Okay, let me try to get the CERs. Okay. Is it going? Yeah. Okay. All right. So this one, again, in talks with kids after school, we think, maybe the question kind of wasn't right. Okay. Right. Maybe we should have said something like, what factors affect the elastic potential energy? Okay. So just do your best with this because we're learning this too. Okay. All right. All right. So here, make sure in your claim, make sure you have the equation for EE. Oops. Kx squared, and then what the slope represents. Okay, remember that's the spring constant. I'm just going to say that, and then you can go back and look and figure it out. Okay, if you want to state this a little bit differently and kind of rework the claim and evidence, that's totally fine, because like I said, this is the first time we wrote them this detailed, and in writing them and talking to kids about it after school, it's a little harder than we maybe thought, and I think we're not asking quite the right question. So just do your best, it'll be fine. As long as you're explaining everything somewhere, you should be good, okay? Evidence, remember, don't explain. The main thing we want is do not explain in the evidence, just what you see, okay? So you can say what you saw, how the graph looked, right? You could say what it's measured in, whatever, but you should not say, like, the slope tells me the spring constant. No, you should just say, the slope is 16 newtons per meter, okay? You may say, I noticed other groups had different slopes than I did, right? You could say that. That would be good, okay? And basically just what you saw the relationship was direct, you saw that the graph is a line, you can say stuff like that, okay? Reasoning, right? This is going to be the real good part. This should be the real part where you're really explaining everything. Okay? What does the graph tell you about the force to stretch a spring and how much it stretches? So basically you're trying to explain, if I want to stretch the spring further, what does that mean about the force required? The more I stretch the spring, what happens to the force? This is just restating what the graph is telling you. Okay? Here again, I want you to explain the slope of the graph, all right? So what is it called? What is its letter, right? What does it mean, all right? And how would changing this affect the force needed to stretch the spring, okay? So this is kind of important. All right, so if I had a slope like this, okay, or a steeper slope like this, and let's say we're gonna stretch them to the same spot, okay? So keep it the same. Okay. Which one is a stronger spring? And then what does that do? Okay. So, right. So let's say this one takes 2 newtons per meter, and say this one takes 4.